the next talk, Professor Jeff Krichmar from UC Irvine. So Jeff.
Great. Thank you, Hirak. And I'm the last speaker, I think, of the day. So it's been a wonderful day. I just want to say before I get started, all the talks and including the posters have been really interesting. So thank you, especially Hirak and Kashin for organizing this.
Jeff, you can take 30 minutes. Sorry, you're starting late.
That's okay. We'll see. Just cut me off if I'm going too long, but I don't think I will. So I'm going to talk about motion processing in the primate dorsal visual stream. And it nicely, I think, complements Bruno's talk, the last talk. And really, this is work by Kashin Chen and Michael Baylor. And there's a paper coming out on the work I'll kind of towards the end of this be talking about that'll be coming out very soon in Journal of Neuroscience. So let's get into it. Like Bruno was just talking about, sparse efficient coding. So the nervous system is under really tight energy constraints. So you have to represent efficient information efficiently. And I think this is particularly important for motion information, complex motion patterns, that you have to respond rapidly to those and appropriately. And I'll give you maybe a real world example why that's the case. Oh, I didn't want to start there. So if you're being chased by dinosaurs, you really have to process the motion so you can avoid things. And there's tons of motion, not only the dinosaurs themselves, but your own. And probably more day-to-day things are very important to respond rapidly and appropriately. And where does this happen? Well, the dorsal, quote unquote, wear stream in visual cortex is important for handling motion cues. And just kind of give you a brief overview. You have information coming in from the eye. It goes through the retina and the thalamus, and then to primary visual cortex, which was just talked about. And the areas that I'm going to talk about are area MT, which processes very local motion cues, retinal flow, optic flow. And then that projects strongly to an area called MST, which responds to much more complex motion patterns over a larger field size. And like I said, this has to be happening very quickly and very efficiently. And then those project to decision areas like the parietal cortex and other areas. So how does this happen? And I don't know if dinosaurs, I very much doubt, given what I know about dinosaur neuroanatomy, that it has a visual cortex, but I'm sure the dinosaurs had to have something, a homolog to this to actually process motion information quickly, given their behaviors in Jurassic Park. Okay, so two ideas that come out of this to reduce the amount of processing and energy or sparse coding and also dimensionality reduction. So if you had a completely sparse code, it'd be local. And you'd have these things like grandmother cells, but you wouldn't get much reuse out of this. It could only encode represent one thing. If you have a dense code, you're utilizing a lot of neural activity. So somewhere in between, you want a sweet spot that's sparse. And another concept is the difference between holistic, putting together a whole face, or parts-based, by reusing parts of the image or parts of a scene to actually reconstruct information. And so both of those ideas are energy efficient and reduce the dimensionality of the problem. And a few years ago, Michael Baylor did some very nice work looking at a machine learning technique called non-negative matrix factorization. And he took, instead of what was originally used for earlier was building up reconstructing faces, he took optic flow information and had a bank of filters that responded very much like area MT on the local flow fields. And then he injected that into non-negative matrix factorization. And lo and behold, you got, these are the weight vectors from the original flow image, MT image, to this matrix here that we're calling similar to, or has homologs to MST. And you see these weight vectors that look very much like MST receptive fields. And this is a nice way to do dimensionality reduction because you have a large feature space of all the different speeds and directions, and you have a large library of stimulus exemplars, and you can take this very large matrix and reduce it by a smaller number of basis vectors times the feature and the small number of basis vectors across the stimuli. And from that, and you see, and hopefully you see my mouse, a sparse number of neurons or a sparse number of units are active, and that's sufficient to reconstruct this image. So this kind of gave us an idea that if MST has these complex responses that fall out of this, enforcing this dimensionality reduction technique for machine learning, that maybe that's something that the brain is doing. But at this stage, it remained to be shown how you could do this in something like a neurobiological circuit with something that is more biologically plausible to do the equivalent of this non-negative sparse coding. And this is where Kashin Chen actually took this idea and made it more biologically plausible. So she implemented a spiking neural network model, and she evolved the spike time independent plasticity and homeostasis parameters. And I'll explain exactly what those are if you're not familiar in a moment. But let's just look at the kind of overall architecture. So you have, again, flow patterns, and you have a bunch of MT neurons that have different directional tuning and speed tuning, just like real MT neurons. And these are now spiking neurons. And they project with plasticity to an excitatory inhibitory area that we're calling MSTD. And from the weights here, we can reconstruct, or we can get a pattern that initially will not be like the original pattern, but what we can do is use an evolutionary algorithm to have a fitness function, and the fitness is how close the output here, the prediction, matches the original flow pattern, actually the original activity of MT to that flow pattern, okay? And this is a very large, can be a very large weight matrix. So rather than evolving the individual weights, which would take a long time and be a hard optimization problem, we optimized the learning rule. And there's a theoretical reason for that, but I'll get to that later on. So what we optimized, or she optimized, was the parameters for STDP, which if you know STDP, if you have the presynaptic activity before the postsynaptic activity, you get LTP. If you have the opposite order, then you have LTD, long-term depression, long-term potentiation, long-term depression. And what dictates how much potentiation or depression you get is the amplitude of this curve and the time constant of this curve. It starts to fall off if those two events are further away in time. And then there's, for the depression part, there's an amplitude for the minus part of the depression and a time constant for that. So for each projection, there were 4 parameters. And we have found that STDP on its own has stability issues. So we and others have added homeostasis kind of function, in our case, synaptic scaling, that pushes the weights, overall weights of a projection to a target firing rate for the postsynaptic neuron, right? And that's what I'm calling STDP-H. And to give you some details of what was done, we took a spiking neural network. We were evolving those parameters. So, and we had 50 separate instances or individuals. So we had to run this in parallel on a simulator called CarlSim. And we generated a whole bunch of flow fields and randomly held out some for validation and did sort of like Monte Carlo as you go through different generations. And I won't go into the details of this. We can talk about it later if you want specifics, but there were only 19 parameters per individual that you had to search for the ideal values of, and it ran for 30 generations. And we used a form called evolutionary strategy that we can talk about a little later. And the bottom line is, with different sizes of MST pools of neurons, we got very good fits. So these are basically the correlation between the original MT pattern and the reconstructed MT pattern. And the B equals 64 means there were 64 neurons in the MST population. And you could see correlation values that are very high once you get beyond like a small network of 16. And then on the right, you see the learned or evolved STDP parameters. And if you know anything about STDP, this has a very biologically plausible shape as well, where you have a larger area under the depression and a fairly tight time constant of the drop off, especially for the potentiation of how quickly it goes down. And then also if there was STDP on the inhibitory connections and the signs of the curve are flipped, which makes sense also biologically. So the bottom line is, under all these cases, it seemed to converge to similar solutions of these STDP parameters. And I'm not showing it, but also the homeostasis parameter firing rates. So we got good fits. This is just a representative example to show you what comes out of it. So you have the original pattern, you have the MT to MST connection weights, and you see these complex patterns that are spirals, that are translation, that are expansion, very similar to what you see in recordings in MST. And you see the activity to reconstruct which neurons would be active. And this is an example with 64 MST neurons. And that's a fairly sparse code, actually, to reconstruct the original input. And we did look at the sparseness. So we looked at, I just showed you an example of a population sparsity with the different size MST populations. And also there's lifetime sparsity, shows good lifetime sparsity as you get to more and more neurons, but not too many, that over all the stimuli that are presented to it, you get a subset of neurons, the neurons only firing for a subset of stimuli. So both population and lifetime sparsity come out of this, emerge out of this model. And after the model was trained and tested, then we gave it data sets from actual studies where they recorded from this brain area, MST. And so we used now new stimuli that were used in recording from monkey MST. For example, this work by Takahashi et al. And they found single neurons that responded to rotation and translation, having one neuron responding to multiple things of rotation and translation. And we also found neurons in our model that responded to rotation and translation. Looking at the total population, they found neurons that responded to the azimuth for lateral motion. I think the way to read this is more neurons responded to 180 or 0360, which would be the lateral motion. But if you look at the azimuth, I look at the elevation, you have more neurons responding to all elevations. And we saw a similar pattern in the spiking neural network model for this as well. So it nicely shows some of the responses and population responses and also individual neuron responses that you would see in real MST. Looking at another data set by Gu et al., in this case, the arrows mean the direction of selectivity of MST. So they found more neurons responding to when the monkey perceived moving forward, and these bands on the left and right are when the monkey perceived moving backwards. And if you looked at the direction selectivity of our model, you see the similar pattern. So it is picking up, given the inputs that they used in this study, the model is also picking up that kind of selectivity. So it's responding very much in that way like MST. And then the question is, well, what would you use these patterns for? Well, it seems like from MST, you'd also want to have a kind of behavioral parameter like encoding the heading or the focus of expansion. And so you see this cartoon drawing of a monkey moving through space with its head turned and its eyes rotated. As you're moving through space, the optic flow will expand, and the focus of that expansion would be where the animal was heading. And so how well, given a pattern like this, can the model predict the focus of expansion? And so we used a linear estimator to take the weightings from MST to a couple of parameters to try and learn the XY coordinates of the focus of expansion, generate a bunch of optic flow fields, and did a whole bunch of 10-fold cross-validation. And comparing it to a previous model that did this with templates for the MST, like just picking out things that they thought MST would do and having templates, the spiking neural network model did much better as far as its focus of expansion error and for the X and Y coordinates. And this was not just with size of MST is 64, but with across all the populations we looked at. So this also is an efficient way of maybe encoding and then decoding behavioral parameters like focus of expansion, or I can imagine some other important motion cues that you could use this representation to actually encode. All right, so let me wrap up with some thoughts about what this means. First, just what we did was we demonstrated a model of MST was able to account for a lot of these properties observed in monkeys. And we've done that now with non-negative matrix factorization and now with a spiking neural net that has a biologically plausible learning rule. And you find tuning to spiral motions, you find 3D translation and rotation, and you find encoding of perceptual variables such as heading. And I would imagine others if we do that. Now, the MSTD neurons learned a compressed and efficient and reduced representation of self-motion. And we were fairly agnostic to this. We just had it learn, evolve the parameters of spike timing dependent plasticity plus homeostatic scaling. And so we are operating under the hypothesis that maybe this is what STDPH is doing in the brain to actually get these efficient, reduced and sparse representations. And maybe other neurobiologically plausible plasticity could also be doing this. But STDP and homeostasis seems to have a very good way of actually kind of cutting out what's not needed, and the scaling also keeps the activity within range. And I think in general, this is a novel modeling approach that rather than hand tuning, manual tuning, or rather than searching over weights, you can evolve the learning parameters. In a complicated situation like this, this was kind of the only way we could actually come up with a solution. And so it's basically learning to learn or evolving to learn, which I think is an interesting concept as well. And lastly, going back to what this conference is about, or this workshop's about, what can computer vision learn from sparse reduced receptive fields? Well, real neurons spike. So why do they spike? And I've had arguments with people over the years, but I think the main reason neurons spike is to conserve energy, and that's not lost on a lot of hardware engineers. So they spike, and they don't spike too often, and between spikes, they're not taking as much energy. But another important thing, especially for, I think, this problem of dealing with complex motion patterns, is they respond in a very timely manner. They respond very quickly. So sparse reduced spiking representations can conserve energy by reducing the number of action potentials, and I should have said also reducing the number of neurons needed to respond to stimuli. And this would be critical for many vision tasks. And just getting an idea, this is not lost on neuromorphic engineers, and this could be embedded because it's in this spiking domain and take advantage of neuromorphic hardware. And I'm showing not this model, but when we were in Telluride a number of years ago, we were working with the engineers from IBM True North at a very early stage for their chip, and we put their chip on one of our robots, and the convolutional neural net was just trained to learn to stay on the path and not go over the edge and down the mountain. And what's striking to me about this was the robot was using a small nickel metal hydride battery to run, and they hooked up the True North to that, which was running the convolutional neural net. And so this closed system was using very little power. We ran this up and down, and this is a very steep trail. It doesn't show in the video, but we ran this up and down this trail for about an hour on one battery without having to recharge and running everything. So I think, and Bruno was talking about this too, I think this is thinking about things in this way and having this pathway and looking at some of the tools to actually get these low power, small, what do we call it? Swaps, small weight and power systems that can be used in embedded applications, I think is very important. And also it may say something about what the brain is doing and why it's so energy efficient and why it evolved to have these energy efficient representations. So I will stop there except to highlight the people that did the real work, which is Kaixin Chen, did all the spiking neural network work, and she worked with Michael and I. Michael did the original non-negative matrix factorization idea, and then she worked closely with Michael to get started, and then she really took off to do this work, and of course our funding agencies. And I will stop there and take any questions. Thank you for your attention.
Thank you, Jeff. That was a great talk. Is there any questions?
Yes, I have a question.
Okay.
Yeah, hello, Jeff. Yeah, very nice talk. I like you use the motion processing in MSTD and a spiking network as an example to study some general principle. So actually, my question is a little bit beyond what you have talked in your talk. So I noticed that you cite the Takahashi's result, and I also know like MSTD is not just a visual area, but it also a multisensory area. It could use the visual and the vestibular input to do the motion processing. And I know in his work, he found some neurons, which show opposite preference of the rotation. So I'm wondering whether you have some thoughts about this result, or your network model is able to explain that.
Yeah, I have thoughts, and our network model cannot explain that, but that's actually a very important point. MST is multimodal, so it is getting vestibular information. We didn't have vestibular information to put into this model, but that is extremely important for the problem too, because you imagine while you're moving through space, you're also getting vestibular information, and sometimes it was either Takahashi or it was another study. There's very few studies that can do this. Sometimes you can confound that, where your visual motion is not actually the same as your actually body motion, and you get interesting results. So that is something I would like to build in, especially if we did embed this model on a system that was moving through space, like a robot or a drone. I think that'd be a very important cue to take into consideration. Yeah.
Okay, thank you.
Can I expand on that, if you don't mind, Chef?
Sure.
As I know, so in Greg DeAngelis and Dora Angelaki's lab, they're still studying that. And one idea is that these neurons with opposite preferences, visual versus vestibular, could help you with flow parsing to kind of disambiguate which flow is from your own motion and which flow is actually from an object moving independently of you.
Yeah. Oh yeah. Thank you. That is a good point. So you're moving, but objects are moving, and so like if you want to disambiguate your own movement from some object that's moving, like that dinosaur, then that might be a way to actually make that calculation. Yeah.
Sure.